Hello, welcome to all. In today's class, we are going to see what is a transducer, what are the classifications of transducer, and the construction and working of an inductive transducer, which is nothing but LVDT, linear variable differential transducer. Before seeing what is transducer, we will see what is the need for a transducer. So, in electronic measurement system, we are having a measuring device. So, the measuring device will be given an input and we will give the output. So, in general, an electronic measurement system has three components. One is the input device. So, the input device receives the measurand or the input signal. So, the input device receives the measurand or the input signal. Second one is the signal conditioning or processing device. The signal conditioning or the processing device do process over the signals like amplification, modulation, filter and attenuation. And the third component is the output device, which gives the results of the quantity which is to be measured. Now, we know that the measuring device, we have the three components like input device, signal conditioning or processing device and the output device. In most of the measurement system, the measurand is the non-electrical quantity and most of the techniques uses an electrical quantity. So, there is a need for a device which converts a non-electric quantity into an electrical quantity. So, the device which is used for converting that non-electrical quantity into an electrical quantity is called a transducer. Now, let us see the definition of a transducer. What is transducer? So, the device which converts a physical quantity into proportional electrical signal is called a transducer. The device which converts a physical quantity into the proportional electrical signal is called a transducer. Or in another way, we can define the transducer as the device which converts one form of energy into another form of energy. One form of energy is converted into another form of energy. So, the device which is used for this conversion is called as a transducer, and the process of converting this energy from one form to another form is called as transduction. So, transduction is nothing but the process of converting the energy from one form to another form is called as transduction. So, what is a transducer is which converts a physical signal into proportional electrical signal. Now, let us see what are all the electrical transducers. In general, the transducers are classified into electrical transducers and mechanical transducers. Now, let us see what is an electrical transducer. So, the electrical transducer has two components. One is the detection or the sensing element. Generally, sensors will be used for detecting or sensing the element, and the second component is the transduction element. These are the two components in a electrical transducer. Now, let us see the block diagram of an electrical transducer. So, the block diagram of a transducer, has a sensing element which senses the non-electrical quantity which is to be sensed, and the sensor response will be given to the transduction element, and the transduction element will convert the non-electrical quantity into an electrical signal. So, the work of the sensing element is it senses the physical quantity or the rate of change is sensed with the help of the sensing element, and the response of this sensing element is given to the transduction element. What this transduction element will do is it will convert the non-electrical signal into a proportional electrical signal. So, this is a basic block diagram of a electrical transducer. Now, let us see the classification of transducers. Generally, the transducers are classified into four types as active and passive transducers, analog and digital transducers. Third one is transducers and inverse transducers. The fourth one is primary and secondary transducers. So, generally we have four types of transducers: active and passive transducers, analog and digital transducers, transducers and inverse transducers, primary and secondary transducers. So, the output of this transducer will be an electric signal. So, electrical signal produced may be either a voltage, current or frequency. Now, let us see what are all the passive transducers. So, in electrical circuits we have many combinations of passive elements. It is mainly 3 passive elements like resistor, inductor and capacitor. In electrical circuit, there are 3 combination of passive elements like resistor, inductor and capacitor. So these are described with the help of a parameters like resistance. Inductor is described with the help of a parameters like self and mutual inductance. The capacitor is described with the help of capacitance. So in order to obtain the electrical signal from these transducers, we need external power. So for passive transducers, we need external power to get the electrical signals. So any change in these parameters like resistance, inductance and capacitance is observed only when external power is given to this transducers. So this based on these 3 parameters, the passive transducers we have resistive transducers, and the second one is inductive transducer, and third one is capacitive transducer. So we have 3 types of transducers: resistive, inductive and capacitive transducer. First let us see what is inductive transducer. These inductive transducers are the most simple and popular type of displacement transducers, in which the variation of inductance as a function of displacement is achieved by varying the self or mutual inductance. So this inductive transducers are the popular type of displacement transducers in which the inductance acts as a function of displacement, which is achieved by varying the self and mutual inductance of the coil. We know that the self inductance, which is represented as L, is equal to N square by S, where N is the number of coils and S is the reluctance of the coil. Also we know that the reluctance S is equal to L divided by mu into A, where L is the length of magnetic circuit in meter and mu is the permeability of core Henry per meter, and A is the area of magnetic circuit in meter square. Now if you substitute the value of reluctance in this self inductance L, you get L is equal to N square mu A divided by L. So the variation in the self inductance is due to, you can vary the self inductance by varying the number of coils. So by changing the number of coil N, we can vary the value of self inductance. Next, change in reluctance S also changes the value of inductance L, and change in permeability also changes the value of L. So the self inductance can be varied by varying these components, that is number of coils, reluctance and the permeability of the medium. Next one is the mutual inductance. You know that mutual inductance is represented as M is equal to K into root of L1 by L2. K is the coefficient of coupling. Here L1, L2 are the self inductances of the coil. So the mutual inductance M can be varied by varying the self inductance of the coil L1, L2 and the coefficient of coupling K. So we can vary the self inductance by varying these 2 parameters, coefficient of coupling and the self inductance. Now let us see a most popularly used type of inductive transducer, which is nothing but linear variable differential transducer. It is generally called as LVDT. We can also say it as linear variable differential transducer or linear variable differential transformer. Linear variable differential transformer or linear variable differential transducer. It's the most widely used inductive transducer which is used to measure the displacement. Widely used inductive transducer used to measure the displacement is the linear variable differential transformer or transducer. So it is a inductive transducer. We have seen what is an inductive transducer. So inductive transducer, it means the change in inductance of the coil due to which non-electrical quantity is converted into electrical quantity. We know that inductive transducer, the change in inductance of the coil is used for transduction, that is, it converts a non-electrical quantity which is nothing but displacement here, it is converted into an electrical quantity. So here the displacement or the linear motion is measured in terms of output voltage. So displacement or linear motion is measured in terms of output voltage here. So the differential linear variable differential transformer, why we are calling it as linear is it converts the linear motion or the displacement into an output voltage. Why we are calling it as transformer is that here we are having a transformer which has one primary winding and two secondary winding. So a transformer will be used here, so we can call it as a linear because of measuring linear displacement, and the transformer is we are having the primary and the secondary winding. Why we are called it as differential transducer is, so differential is used because the output voltage which we are getting is the difference of the output voltage across the secondary windings. So the difference in the output voltage across the secondary windings will be the output voltage of this linear variable differential transformer. So the output will be a differential voltage across the secondary windings. So we are calling it as differential transformer, and since we are having primary and secondary windings, we are calling it as differential transformer. It converts linear motion into voltage, so we are calling it as linear variable differential transformer. Now let us see the construction of linear variable differential transformer. So in the construction of linear variable differential transformer, here we are having a primary winding in the this represented as P, and we are having two secondary windings here. This one is the secondary winding 1, this is represented as S1, and this one is the secondary winding 2, which is represented as S2, and a soft iron core will be placed in between the primary and the secondary, which is attached to a arm where the displacement which is to be measured is given. And this primary and secondary windings will be wound on a coil former, round former. So, in the construction of LVDT, we are having one primary winding and we are having two secondary windings. Primary winding P, secondary winding S1 and S2, and these windings are wound on a cylindrical form. Here in this diagram we can see the primary winding and the two secondary windings, and the two secondary windings will have equal number of turns and will be placed and they are identically placed on either side of the primary winding, and a soft iron core will be placed in between the primary and secondary winding, which is free to move in between the primary and the secondary winding, and it has an arm where the displacement which is to be measured is applied to the soft iron core. So, the soft iron core is placed between the primary and secondary winding. And the displacement which is to be measured is applied to the arm which is attached to the soft iron core, and this primary winding will be excited. Primary winding represented as P is excited by an alternating voltage. An alternating voltage will be supplied to the primary winding of the LVDT. So, on the construction we are having one primary winding and the two secondary windings, and these windings are wound on a cylindrical form. The soft iron core which is placed in between the primary and the secondary windings, and the displacement which is to be measured is applied to the arm which is attached to the soft iron core, and the primary winding will be excited with an alternating supply. Let's see the working of LVDT. Since we know that the primary winding is excited by an alternating current source, it produces alternating magnetic field. So, primary winding excited by an alternating current source, it produces alternating magnetic field. This alternating magnetic field which produces alternating current voltages in the two secondary windings. So, the output voltage of the secondary winding is given by secondary winding S1 has the output voltage ES1 and secondary winding S2 has the output voltage ES2. So, to get single output from the secondary windings S1 and S2 into a single voltage signal, these two secondary windings S1 and S2 are connected in series opposition to each other. These two secondary windings are connected in series opposition, so then we can get a single output from the two secondary windings S1 and S2. So, the differential output voltage from the secondary windings given as E0 will be equal to ES1 minus ES2. So, the E0 will be equal to ES1 minus ES2, that is the difference between the voltage across secondary 1 and the secondary winding 2. Let us see the circuit diagram of an LVDT. So the LVDT has a primary winding. In between the primary and secondary there will be a soft iron core with arm, and the secondary is divided into two. Have two secondary windings, S1 and S2, which produces the voltages ES1 and ES2. So in order to produce a single output voltage, these two secondary windings are connected in series opposition, so that the differential output voltage will be available across this two secondary voltage, that is E0, which is equal to ES1 minus ES2. This one is the soft iron core. Primary winding, which is supplied with the help of a AC source, and the displacement which is to be measured is applied to the arm attached to this soft iron core. So this one is the circuit diagram of LVDT. Now let us see the working of this LVDT. Since the AC excitation is given to the primary winding of the LVDT, it produces an alternating magnetic field. So the flux produced in this primary will link with the secondary S1 and ES2, which in turn produces the alternating current voltages ES1 and ES2. Since this two secondary windings are connected in series opposition, we will get a differential voltage E0, which is equal to ES1 minus ES2. The output voltage, that is the differential voltage E0 across the secondary, varies according to the displacement of the soft iron core. Now let us consider the soft iron core is at null position. When the core is at the null position, the flux linking with the S1 and S2, that is secondary winding S1 and S2, flux produced in the primary which links to the secondary winding S1 and S2 will be equal. So the voltage induced across these secondaries S1 and S2 also will be equal, that is ES1 will be equal to ES2. So the output voltage E0 will be equal to 0 when the core is at null position. Now if you move the core to the left of the null position, this core is moved to the left of null position. The core is moved to the left of the null position. The flux linking with the secondary winding S1 will be more compared to the flux linking with the secondary winding. Since the flux linking varies, the voltage induced on the secondaries also varies. So when the core is moved to the left of the null position, the secondary voltages ES1 will be greater than ES2. So the output voltage V0 will be equal to ES1 minus ES2. So the output differential voltage E0 is in phase with primary voltage. Now when the core is moved to the right of the null position, the core is moved to the right of the null position, the flux linking with the secondary windings will be more compared to the flux linking with the secondary winding S1. So ES2 will be greater than ES1. So the differential voltage E0 will be equal to ES2 minus ES1. So the output voltage is 180 degree out of phase with the primary voltage. So the amount of voltage changes in secondary windings S1 and S2 is proportional to the amount of movement of the core. It depends on the amount of movement of the core, whether the core moves to the left or right of the null position, the amount of voltage across S1 and S2 changes. So this indicates the amount of movement of the core indicates the linear motion of the linear motion or linear displacement of the core. So by noting the output, which output is higher, the direction of movement of the core can also be determined, and the amplitude of the output voltage will be a function of the distance of the core moves, while the polarity of the phase indicates the direction of motion of the core. So therefore the amplitude of the output voltage, it is differential voltage produced, will be a function of the distance the core moves, while the polarity of the phase indicates the direction of motion of the soft iron core. So the output voltage of LVDT is a linear function of core displacement within a limited range, that is up to 5 mm from the null position. We will get a linear characteristics. Now let us see the characteristics of LVDT. If you draw the characteristics of LVDT, this displacement, output voltage, this is A naught. So 0 indicates the null position. The output voltage of LVDT is a function of core displacement within a limited range, that is up to a 5 mm. The characteristics will be linear, which is indicated with the distance OB and OA. So this one is the linear range. Beyond 5 mm, it will become, the curve will become non-linear. So at null position, the output voltage is 0 because the difference in the secondary voltages is equal, but there will be a small voltage which occurs at null position. That voltage is called as residual voltage. So from OA, O to A and O to B, that is 5 mm from the null position, that is OA to OB, the characteristics will be linear. After that it will become non-linear. So after OA and OB, the characteristics will become non-linear. So within the limited range of 5 mm from the null position, the characteristics will be linear. Ideally, the output voltage at null position O will be 0, but practically there will not be 0 voltage at null position. There will be a small amount of voltage at null position. That voltage is called as residual voltage. The small voltage at null position is called residual voltage. So what is this residual voltage? Why this residual voltage occurs? So this residual voltage is due to the presence of harmonics in the supply voltage. So due to the presence of harmonics in the supply voltage, this residual voltage occurs at the null position, and also due to harmonics produced in the output voltage, on account of use of iron core, either an incomplete magnetic or electric unbalance will occur, which produces the residual voltage. Generally, the value of this residual voltage will be less than 1% of the maximum output voltage of the LVDT. Now let us see the advantages of LVDT. First one is the high range. So high range of displacement can be measured by using this LVDT, that is from 1.25 mm to a displacement of 250 mm can be measured with the help of this LVDT. And also 0.25% of full scale linearity can be obtained, that is up to 0.003 mm minute range of displacement can also be measured with the help of this LVDT. So the LVDT has an higher range. Second one, friction and electrical isolation. So in LVDT we can see that there is no physical contact between the core and the coil, so it is frictionless device. Since there is no physical contact between the core and the coil, there is no friction between this core and the coil, physical contact between the core and the coil, it is a frictionless device which produces so there will be no wear and tear of the device, which also causes no damage to the parts. So it has an infinite mechanical life. So the frictionless device has no wear and tear of the device and do not cause any damage to the parts of the LVDT, which gives an infinite mechanical life. And third one is immunity from external fields. So there is a separation between coil and core, which permits external environmental conditions like temperature, pressure and vibrations does not affect the LVDT. So since there is a separation between the core and the coil, the external environmental conditions like temperature, pressure and vibrations does not affect the parts of the LVDT. Generally LVDT will be sealed in a steel iron box. Fourth one is high output and sensitivity. So the LVDT gives higher output, so does not require any amplification after output. So it requires only less amplification. So there is no need for amplification in case of LVDT, and the sensitivity of LVDT is about 300 millivolt per mm. That is, for 1 mm displacement will produce a voltage of up to 300 millivolt. Fifth one is rigidness. So LVDT is mechanically rigid. It is mechanically rigid. So it can withstand mechanical vibrations and shocks. So it can withstand the mechanical vibrations and shocks. And the sixth one is low hysteresis. So the hysteresis effect is nothing but if we give an input to the device, we are getting an output. If we keep on increasing the input, we will get the output, but if we decrease the value of input, we will not get the same effect of input. So this hysteresis is low in case of LVDT. So this low hysteresis gives good repeatability of measurement, because if the hysteresis is more, means the output is, varies according to the input. If the input is increased, we will get an one output. The same input is decreased, we will get an another input. So the curve will not follow the same path. So the repeatability of the readings is not possible if we have high hysteresis. So that is less in case of LVDT. And the seventh one is low power consumption. So it can consume less than 1 watt of power for its operation. So the consumption of power is low in case of LVDT. So we will see the disadvantages of LVDT. So first one is the large displacement can be measured, which leads to a large amount of output voltage. So the large displacement produces large amount of voltage, which is difficult to measure by using LVDT. So it is difficult to measure large displacement which produces large amount of voltage by using LVDT. Next one is, this LVDT is sensitive to stray magnetic or electric field. It is sensitive to stray magnetic and electric field. Third one, temperature affects the performance of this LVDT. So the performance of this LVDT is affected by the temperature. And fourth one is, the dynamic response is also low in case of LVDT because of the mass of the coil. The dynamic response is low. Next, we will see the uses or the applications of LVDT. First application is, it is used in all applications where displacement ranging from few mm to few centimeter is to be measured. So it acts as a primary transducer. The first application is, it acts as a primary transducer where the displacement ranging from few mm to few centimeter can be measured. Next one is it acts as a secondary transducer. It acts as a secondary transducer. So, the secondary transducers are used to measure the force, weight, pressure, etc. So, by using secondary transducers, we can measure force, weight, pressure, etc. First, we have to convert this quantities like force, weight and pressure into displacement by using the primary transducers. So, the primary transducer will convert all the quantities like force, weight and pressure into displacement with the help of primary transducer. And second, this displacement will be converted into a electrical signal with the help of LVDT. So, it acts as a secondary transducer. Then this displacement applied to the LVDT that acts as a secondary transducer. So, it converts the displacement into proportional output voltage. The displacement will be converted into its proportional output voltage. So, the applications of LVDT, it acts as a primary transducer and a secondary transducer. The primary transducer, it converts the quantities like force, weight, pressure into an displacement. And while acting as a secondary transducer, first it converts the quantities like force, weight and pressure into a displacement. Then the displacement will be applied to the applied as input to the LVDT, which acts as a secondary transducer and convert that displacement into a proportional output voltage. Thank you.